Okay, now we're gonna implement Prim's algorithm in Python. We're gonna start off by uh, creating a class for holding our vertices. Okay, class vertex. Now, our vertex class, let's write the constructor, and so that we will be able to identify each vertex, we're gonna give each of them a name. Also, our vertices are going to hold weights, okay, as well as edges. We could do a self dot adj for adjacencies, and within this we could hold pairs, which would be the vertex that is the adjacent vertex as well as the weight. Okay. Another approach we could take, which I think might even be better, is we could use a dictionary. Okay. Yeah, let's use that approach. We're gonna hold our vertices, our adjacent vertices in a dictionary, and the value that would be associated with each vertex would be the weight of the edge connecting the two vertices. Also, according to our algorithm, we are going to set a key value. Let's see, float. Okay. This is the way to get the maximum value, maximum positive value in Python. And we are also going to set the predecessors. Good. Now we are going to define a way for adding edges. And that would take another vertex as well as the weight of the edge. And what we would do is we would add that new entry to the dictionary, and since the edges are not directed, we also want to do, we also want to add uh, the edge in the other direction from the other vertex. Well, let's say it's a dictionary, so we would use the colon in between the name value pair. Okay, good. Now we can go ahead and add the various vertices as well as the edges. Now we're going to name the vertices. We're going to give them names that correspond to these lettering that we have on this right side. So we're going to say VA is equal to vertex A, VB is equal to vertex B, etc. Now we want to add the edges. We're going to say VA dot add edge VB, comma 6. Add this edge, and we're going to go ahead and add the other edges. VA dot add edge VC, comma 7. And okay, once we've added the edges, we're going to make the graph, which is a set of the edges, a collection of the edges. Okay, so our graph is V on this. Okay, now we're going to go ahead and write Prim's algorithm. It's going to take a graph. W is supposed to be the set of weights, but we've already incorporated those weights into the information that the vertices have. So we don't need to pass it separately. And we're going to pass a root vertex. Now, in creating the vertices, we've already set the key values to infinity as well as the predecessors to nil. So this is what we haven't done yet. We could do it outside, or well, we can do it inside of the algorithm. We're going to say root dot key is 0. And we are going to create a queue. Now, priority queue, the priority queue data structure in Python is within the queue module. And we're going to add the vertices to the queue. Now we use the put method of class priority queue to add items to the queue, and we use the get method to get them out. Now we're going to check whether the queue is empty. Priority queues have an empty method which will return true or false. We're going to call U current vertex. Now, just so that we will know what's going on, let's print some stuff here. Good. This is just to help us see what's going on. Okay, it's not really part of the algorithm as such. The next thing we're going to do is we're going to go through each vertex that is adjacent to the current vertex. Now, since we're holding the vertices in a dictionary, we can get both the vertex and the weight at the same time. Okay, from a dictionary, I'm going to say for what did we call it? If Okay, the next thing we want to do is we want to check if the vertex is in the queue, this returned vertex, and we have the weight. We can check that weight by the key value. Okay. Now to check whether something is in, well, in the first place, a priority queue is not iterable, meaning we can't step through the queue and check item by item whether an item is in the queue. Also, we can't use in. It's not like a set where we can say, just as we did here for vertex in graph, that wouldn't work with a priority queue unless we define the in method ourselves. Actually, it would be easier for us to indicate on the vertex whether it is within the queue or not, which with some, you'd see with some algorithms, they'll give a particular color, something like white, gray, and black to tell when a particular vertex has been processed. Okay, so what I'm going to do instead is I'm going to go to the uh, vertex and add a variable which I am going to set to false. Okay, and then once I get the vertex out of the queue, which is here, I change its status. So now I can use this status to know whether um, a vertex is out of the queue. If it's out, then it has been processed. So I'm going to say if vertex means it's out, but if it's in, if not, vertex processed. Okay. And now I'm going to check the weight. we would have gotten the weight from the dictionary. Okay. If that's the case, then we're going to set the predecessor. So the current vertex, and we're going to set the key for the weight. So that looks like it. Okay. Now to see what's going on, okay, we have a print statement here. So let's go ahead and run this. I'm gonna say prim graph, and I am going to pass VA as my root. Okay, we've got a few errors. Name error, VB is not defined. Less than not supported between instances of vertex and vertex. And that's line. That's within the priority queue. Okay, for a priority queue to work, it needs to have some way of prioritizing items, meaning it has to know what is less than something else. And we haven't told our priority queue that explicitly. Okay, so what we're going to do is within our vertex class, we are going to define the less than operator. And being a comparison operator, it should return a value of true or false. So if the current, and we're going to base the comparison on the key value. Good. A, C, B, F, G, D, D, D. Okay, doesn't look perfect yet, but let's see what's going on. Okay. One way we could see what's happening is, let's go ahead and write out a function that is going to print out the minimum spanning tree. Okay, let's see there. I'm going to pass the graph and the particular vertex. Okay, for well, I can't say vertex in graph. Let's say for x in graph if x dot predecessor is vertex, and I am recursively calling this function okay. So we will pass the root, and we would print the vertex, and then a comma, and then we would find its predecessor, print it out, okay, etc. So let's go ahead and run that. Oh, well, we didn't call the function. Okay, we should have said vertex.name. ACBFGDDD. That is obviously not correct. Now, if it were correct, I'd expect we would go from A to B to D to G. So what I'm going to do is first I am going to confirm that we have the right edges and the right weights along the edges. 6, 7. Okay, I think I know what's happening. Okay, here's what's happening. Our priority queue is changing the priority of the various vertices here. Okay, but a priority queue doesn't reorder itself on changing the priority. It only reorders when you add a new item or you remove an item. So I think that's what's going on here. So what we're going to do, we're going to use that. We know that if we add a new item to the queue, it will reorder the queue so that it maintains, it's a proper priority queue. It maintains the item with the least priority at the top. Okay. So we're going to have to add something. Okay, let's do this. We're going to create a dummy vertex. Let's say the dummy. And obviously, once we've created this dummy vertex, it's gonna have a key value of infinity. But what we want is if we should add that dummy vertex, we dot put, and we want to immediately remove it again. You dot get. Now the only way we would know that it's this same dummy vertex popping out is if we give it the lowest key value. Okay, so what we're going to do is, since none of the weights are negative, giving the dummy key a key value of -1 means it's guaranteed that if it's on the queue, it is what will get popped out. Yeah, it should be v underscore. Okay, it's now AB, and then it stops there. Maybe GDD. Okay, let's see if we have some other error. Yes, if you recall, okay, now I noticed something. A, B, C, D. Okay, I have multiple D's here. 1, 2, 3, 4, 5, 6. Yeah, that's more like it. A, B, D, G, C, F. A, B, D, G, C, F. So that's exactly what we would expect. Okay. I pretty much don't need this print out. Okay. And now let's print out the minimum weight. Now to get the minimum weight, what we would have to do, if you recall, the key values, we start with the key values being infinite, but then we override the key values with the minimum weights. So if we should add all the minimum weights, we should have the sum of the weights. Okay, so we're going to print an empty line, because if we run this as it is, um, it, it would print total weights to the right of here. Print without any parameters gives us an empty line. Okay. Graph is not defined. Okay, I'm going to cut all of this out here. And paste it here. And Yeah, I should have defined all of these before. Okay, their total weight is 16. And just to check things, that things are as they should be, I am going to change the position of certain weights and see if we get the correct thing. I'm gonna change this to 4. I'm gonna change this to 7. So A to C is gonna be 4. B to D is gonna be 7. B and I run that, gives me a total weight of 15, and it shows a different um, graph, which would be A to C, B, C, D. Okay, if we add 6 plus 4, sorry, this is not part of it. If we add 4 plus 5, that's 9, plus 3, 11, uh, again, 1, 5 is 9, and 3, 12, 13, 14, 15. That gives us 15. Okay, and this is our new graph. And if we try to see how it comes to that, again, recall that we have a 4 here now, and a 7 here, and we're starting from here. Now the minimum weight going out of 4 is this to see. So this gets a 4. And then the minimum weight going out of these two, A and C, is this. And the minimum weight going out of these three is this. The minimum weight going out of this collection is this. The minimum weight going out of this collection is this. So that's how it works. Good.